In this section, we'll be studying logarithmic functions, also called logarithms. Logarithms are the inverse of exponential functions. Before we look at their definition, let me go ahead and list what we'll be going over in this section. There's three main components. In part A, we'll be looking at the definition of a logarithm. In part B, we'll be looking at graphs of logarithmic functions, and also how to apply transformations to them. And then in part C, we'll be looking at some common logarithms that we'll be using to solve exponential equations and logarithm equations. Now let's look at the definition of a logarithm. We're going to define our logarithms to be the inverse of an exponential function. Remember that every exponential function is one-to-one, and a function being one-to-one allows us to define our inverse functions. Also recall the definition of an inverse function. Now, given these two facts, we can define logarithms to be the following. First, let a be greater than 0 and a is not equal to 1. Then the logarithmic function with base a is defined to be as follows. Here we see that the log base a of x is equal to y, and this occurs if and only if a raised to the y is equal to x. One thing to note here is that the output of our logarithm is going to be equal to the exponent of our exponential. So this is going to tell us something about our logarithm. Since our exponential functions grow extremely large, extremely fast, the reverse is going to happen for our logarithm functions. The more numbers that we put into our log function, and the bigger those numbers get, what we'll see is that our y values aren't going to change much. This means that logarithm functions grow extremely slow. Now let's look at an example where we evaluate a few different values into different log functions. We're going to evaluate the following. Let's start at part A. Part A, we are looking at the log base 10 of 1,000. To evaluate this, we can go ahead and write this as an equivalent exponential. Over here, I'll write my exponential in green. This is going to be equal to 10 raised to the, let's call this value y. So 10 raised to the y is equal to 1,000 here. The y value that makes this true is going to be 3. So y in this case is equal to 3. Again, this is just by definition. Moving on to part 3, again, let's set this equal to y, and then rewrite this using the definition of an exponential. This is going to be 64 is equal to 2 raised to the y. The only y value that's going to solve this equation is going to be 6. This is going to be then 6. Again, this is by definition. Again, we're going to look at part C and part D the very same way. In part C, we're going to set this equal to y, and then we're going to write this as an exponential. We have that ax is equal to ay. And in this case, we know that x is equal to y because our exponential function is 1-to-1. So we get that this is equal to x. This time, in part D, the notation is a little confusing, but we can go ahead and write this again as equal to y. And now we want to write this as an exponent, not as an exponential this time, but as a logarithm. Writing this as a log, this is going to be equivalent to the log of ay, and this is equal to the log of ax. Since logarithms are 1-to-1, again, we get that x is equal to y, which means that this is equal to x. Part C and part D are actually natural properties of our logarithm functions. Let's go ahead and list some other common properties of logarithms. The first property is that the logarithm base a of 1 is always equal to 0. The next property, part B, is that the log base A of A is equal to 1. The third property was the one that we saw in the last example. The log base A of A raised to the x is equal to x. The final property that we want to add is that the exponential A raised to the log of A evaluated at x is equal to x. So we saw the proof for part C and part D. Let's go ahead and look at the proof for part A and part B. Writing part A as an exponential, this is going to be 1 is equal to a to the 0. So this is true for exponentials, which is why it's true for logarithms. Again, using the definition of a logarithm and rewriting it as an exponential, we get that this is going to be a is equal to a to the first, and this is why it's true for logarithmic functions. Let's continue practicing writing our logarithms as an exponential. In part A, we'll be looking at the equation log base 6 of z is equal to 1, and in part B, we'll rewrite the equation log base 10 of 3 is equal to 2t. One easy way to remember how to rewrite this as an exponential is take your base and just push it underneath the right-hand side. Rewriting this as an exponential, this is going to be z is equal to 6 raised to the 1. Again, a very easy way to remember how to rewrite a logarithmic equation as an exponential equation is take the base of your log and push it under the right-hand side of your equation. Rewriting this, we get 3 is equal to 10 raised to the 2t.